So we're going to do galvanic cells and redox potentials. This is a very good experiment for showing you how an electrochemical cell works. And just a reminder, an electrochemical cell is where you're using solutions and metals to make electricity. So on the board I have how you're going to set up your prac. This square box is representing your test tube holder and your two test tubes. You only need two, and each one of the test tubes is called a half cell. So you know what that is. In the first one you're going to have zinc chloride solution, about 10 centimetre depth, and you're going to have a piece of zinc metal, the long piece. Then in the other half cell, these are being held up by a test tube holder. You've got copper solution, 1 molar, they're both 1 molar solutions, about the same depth, making sure your metal piece is in it, and it'll be secured by a alligator clip lead. So once you've got this set up, you need to then set up your salt bridge, which is represented by this green line here. A salt bridge for us is a piece of filter paper that's been soaked in potassium nitrate solution to complete the circuit. And the other thing that completes the circuit is your wire leads that go from the metal electrodes, these are called metal electrodes, to the voltmeter and continue on to make the circuit connecting it to the other metal. So you have a path where electricity can flow, and this is called an electrochemical cell. And what you're going to do, the purpose of this, is you're going to measure the voltage using different metals. And depending on the metals you choose, the voltage will increase or decrease because they have different reactivities. So the one I'm going to show you first is zinc and copper. So this is called the Daniell cell, and you know it because you've studied it. The Daniell cell is a very famous one, Daniell cell, and it's well known to produce in standard pristine conditions where everything is perfect, 1.1 volts. You won't get 1.1 volts, you probably get 0.6 at the most, but we'll see. So that is what I'm going to show you this setup. Then you fill in a table. So you'll do exactly what I show you for these two metals with all your metals. You will fill in exactly what you get. So let's say, for example, you get 0.6 volts here. You look up your textbook or online, you find what the actual should be, and you'll find for zinc and copper it's 1.1 volts. And then you just compare your answer and work out your percentage error. But it won't matter that you have error in your setup because it's not perfect. You'll still get all the metals in the right order because they'll all have the same amount of error, a systematic error. So you'll still get your metals in the right reactivity series. So here we go. You have your two clean, empty test tubes. Here we have the solutions you're going to use. Now don't use the ones in the small bottle because they're not the right concentration. It should be 1 molar and 1 molar. And here are your two metal strips. They're called metal electrodes. And what you should do before you start is get your steel wool and give them a bit of a clean. Now there is some error in this because steel wool will be actually rubbing atoms of iron onto your metal surface, but that's something you can talk about when you're discussing the errors and points of improvement for your experiment. So you can see that's really coming up beautiful and shiny. That's what you want, because then you'll get closer to the actual predicted amount. And if you don't clean off all that oxidative surface, you won't get anywhere near what it should be. The other one, it's very dull, so you do the same thing. Clean it as well as you can. Now the copper's nice and firm, the zinc is quite soft, so it's a thin piece of zinc, so you'll have to sort of do it by pulling away. Try not to bend it. And then you get a nice clean surface. So that's the first thing you do. Then you get your two metals. Now if you can, it's easier. It doesn't matter, you should bend the top over so that it'll stay in place. That's the main thing, stay in place. This one might be a little bit harder to bend. You might be better off bending it before you put it in. You just want to hook it over so it doesn't move. So you've got your two electrodes hanging on the sides. And now what you need to do is you need to fill up the test tube so that the end of your electrode is touching. So you can use this little squirter. I think it might be easier not to, but we'll just see how we go. At least it doesn't spill anywhere. A bit slower. Oh, what have I done? Sorry, what I've done is put the wrong metal in the wrong metal. You've got to make sure you put the copper. I'm glad I made that mistake to show you the copper in the copper solution. Otherwise you're going to get a reaction like that. So you don't want that. So now we have to clean that off. It's only just formed there, so it's very, very soft and easy to get off. Make sure you didn't do what I did just then and put the wrong solution in. So you've got to be thinking and paying attention. So just give that another clean now. So we've got our copper solution in our copper metal, and I'm just going to do the same thing. Now always checking what you're doing. Speaking to myself as well. Zinc chloride, 1 molar. We're going to put it here. We're making sure this is zinc. Yes, right, good. And we're going to do the same thing. So just squeeze that until it goes high enough to get the metal into the liquid. Okay. I think I need to go a little bit higher with the other one. Right. Now, there's your two half cells, but they will not conduct electricity because it's not a circuit. So one of the ways you can make it a circuit is by getting your voltmeter, which you've got two leads. Now how you attach these is they're an alligator clip, and you wind, so this is in your box, in your kit, you wind this up on a screw and then you can just put the alligator clip underneath. You do that for both. You put the black in the black and the red, and you want the most sensitive setting for your, and if it's a bit loose, wind this back down to tighten it while it's on. You want it in the 3, so you want it on these two here, so you're reading the 3 scale, because I think it's going to be a very small amount of electricity that you're making. And you've got to think to yourself, it needs some knowledge. If you don't see the needle moving, you've probably connected it to the wrong one. So we know in the Daniell cell, that's what this is, that zinc's more reactive than copper before we even start. It's the one that should be connected, the zinc should be connected to the black, the negative, because it's the one that's going to be oxidizing and producing electrons. So you just clip it onto your, try not to click your glove on, and then the copper to here. Now that's still not going to move your needle because you have not got a complete circuit. They're not joined in any way. How we do that is we get our salt bridge. This is a piece of filter paper that's already cut in your kit. This is a petri dish. You're going to wet your, so you've got some potassium nitrate solution. It's got all these warnings on it. It's very, very dilute oxidizing agent. Just be careful, make sure you're wearing gloves and eyewear, and you're going to make sure this is saturated in this solution. So you do that by wetting it in the petri dish. Try not to rip it, because if you rip it, you've got to start again. Now this saturated piece then hangs into, you've got to make sure it's into both solutions, but not touching the metal. So it's got to go down the side, stick it to the side, don't let it, it wants to stick to the metal, but don't let it. And it's got to go into solution. And you might have to move your metals around so to get them out of the way. So I can see when I get down low enough, you've got to make sure your metal is not going to bend and touch the paper. Otherwise you're short-circuiting the whole thing. And I can see that I'll need to add some more solution to the copper side because it's not reaching. So a little bit more. And I can see that nothing is touching, so that's good. And also I can see that we have movement on our dial, which is fantastic, thank goodness. And you then have to work out what that is. Now if you move anything, it might move your metal, so make sure as soon as they touch you get a false reading. So you must be checking that the salt bridge is not touching your metal electrodes and that everything is in solution. And now I'm going to make that reading. This is the Daniel cell that should be 1.1. So on this, we're using the 3 scale. So it's tricky. You've got, on the bottom, you've got a 0 to 15. Everyone can see that very easily. And on the top, you've got a 0 to 300. And in the middle, there's a 0 to 3. That's the one we're using because it's the most sensitive. So because we're plugged into the 3, we can just realise that this is 0 and this number is 1. You can see 100, you can see 1 below it, and then you can see 5. We're on the 1 to 3 scale, so that's 1 there. So if that's 1 there, the reading is, that'd be 0.5, so they're 0.1 each, so it's 0.3, 0.1, 0.2, 0.3, 0.3. So it's much worse than I thought. I thought, oh, you probably get 0.6. We got 0.3. Now, as I said, I want to assure you that even though you only got a 0.3 reading, and it's a very high error, it won't, if you do everything the same, you have a systematic error in the system because of our setup and the fact that, you know, a salt bridge that's made out of paper is not ideal, and a whole lot of things that you can actually discuss. So you should be able to get all your metals in the right order of reactivity and write all the half reactions for both metals and also the full equations.